Hi, good evening, everyone. Am I audible to you? Yeah, fine. Uh, my name is Valli. I am the course instructor for this course. Uh, so, in the last class, uh, we have gone through some couple of sessions based on classification of systems and impact. I hope you all are gone through the video lectures of this week. Okay. If you have any doubts, you can ask me, or otherwise, I will quickly summarize the course this week content and then practice some couple of problems. Okay, I'll share my screen. Are you able to see my screen? Yeah, fine. Yeah, in the week two content, in the week one, you have learned about how the typical control system looks like and different use cases of important use cases which are also interesting use cases that Chakravarti sir has explained to you, and then followed by some of the uh, week one we have learned about typical control system looks like, right? Then you understand um, different types of systems like uh, uh, linear, non-linear, time invariant, variant, time variant, causal and non-causal, right? So this so in this week, you will learn more about signals in a control loop, typical signals in a control loop, and then followed by open loop versus closed loop, why you go for closed loop system and open loop system, and different types of signals like analog and digital, continuous and discrete, deterministic and non-deterministic, even and odd, periodic, and all these six signal classifications we have already gone through signals and systems. We have learned all those things, but just a recap of those things here and there. Why we are going to learn all these things? Because that typically the design of controllers depends on the type of the system you are having and what kind of signals you are feeding to the system. So these are the things we need to know before attempting to design a controller, right? So that is the reason we are learning all these tools. For example, if a system is a linear system, then the control technology will be different. The design system.
Ma'am,
Hello.
ma'am, are you presenting anything?
Yeah, I'm presenting.
Screen is showing just black.
Okay, okay.
Yes, and also there are some noises coming.
Um, okay, one second. I'll share again my screen. Now, are you able to see my screen?
Ma'am, it's
Hello. Yeah, fine.
it is visible, ma'am.
Yeah, fine, fine. Thank you. Yeah, yeah. This is the course content. In the week one, you have learned about typical control systems, how it looks like, and then you saw the different classifications of systems, right? And like linear, non-linear, time variant and time invariant, causal and non-causal, and so on. So now in this week, we are going to learn some more things which are needed for designing a system, a control system, like controllers, signals. What are the signals we are used in control loop? Typical control signals in control loop, open loop versus closed loop, signal types of signals, and then you will go with to in the next lecture. In the lecture 2, you will learn about time domain versus frequency domains, and the standard test signals, convolution integral, and system response. Right, in the lecture 3, we have Professor has explained about Laplace transform, properties of Laplace transforms, and typical Laplace transform for typical usually used signals, and so on. Then in lecture 4, you have the professor has explained about the inverse Laplace transform, solutions of ODEs using inverse Laplace transform. Uh, So typically, usually the signal control system will have a plant, right? Uh, this is the plant, and for this plant, you will have a output from the plant. This is the plant response, right? Now, uh, here you will give some input to this plant. Let us say U of t. So here you will have the controller, which actually gives the required actuator signals, that is generates the output that influence your output, and then you will have a reference signal R of t. Then you will measure the output of the signal by using a sensor. Then you compare the output with the reference signal. So this is the error signal. So these are the signals you will have typically you encountered in a typical control loop. Like you will have a reference signal, and then the error signal, which is the difference between the reference signal and the actual output signal, and then your controller signal. That means this is the signal which actually actuates the plant in order to behave in a desired way. So other than these things, you will have disturbances also enter into the system. So this D of t. And sometimes sensors not always measure the actual signal, so you will have here some noise signal also enter. So these are the typical signals you find in control system. Let's suppose if you have a plant like a typical AC in your room. So the objective of the system is you wanted to maintain a temperature at 24 degrees. That means you wanted your reference should be 24 degrees, right? So you want this is the reference signal which you give it to the your AC system. So here the output of the system, that is your room temperature here. So you wanted to maintain the room temperature to 24 degrees. This is the temperature. The room temperature will be measured by a sensor like a temperature sensor. Then the temperature sensor, the output of this signal sensor is compared with the reference signal, and you will generate an error signal. So based on the error signal, the controller gives you a actuator. That means it will directly control the compressor speed. So that will either increase or decrease. Depends on the output of the your room temperature. Let's say, for example, if you switch on the if your room temperature is current at 30 degrees, and your reference is 24 degrees, which you set by remote, right? So then there is a difference of -6 degrees. That is E of t is equal to r of t minus y of t. So here you will have a difference of minus 6 degrees. So that means your controller gives an actuator signal such that it increase the speed of the compressor, so that you will more refrigerant flows through the room. So your room will cool. So based on this, then if it is a room is more chiller than a desired one, then you will get a positive error signal. That means a controller will decide or generate a U of t in such a way that it will decrease the compressor. So then based on this, typically the example, what are the goals of a control system? Basically to track the reference signal. This is also called as servo control. Okay. The second objective of the controller is to reject the disturbances. Another use case of control designing is sometimes the plant is nature itself is unstable. Unstable means if suppose if you give it some input, bounded input, then you will get a bounded output. Then it calls as a stable system. Suppose if you consider an inverter pendulum, so which is having, this is the pendulum, this is the base. So if you give small pulse like that, if you push it little bit, it will fall down. That means the system is unstable. So whatever, even if you give a small signal, the system becomes unstable and behaves which is not in a desired way. So the another objective of the controller is to stabilize the plant. Other than that, another one more objective is, since your plant is not always have the parameters of the plants, you always know it exactly. Sometimes the parameters will change with environment, they change with by aging. So there are, and also you may not measure exactly the what are the parameters of the system. So in that case, the system, your design, your controller should be mitigate those errors, and still it has to behave like a whatever your it is track the reference signal. So that means it has to work against parameter changes, that is sensitive to changes in parameters. Then you have, but designing there are two types of designing. One is open loop control, and the one is closed loop control. Suppose if you are having a plant like this, you are not measuring the output of the system, and just only controller gives a reference signal. If you have a reference signal R of t, and this is your controller, and this is your plant, and this is your output signal. In this case, if you choose controller as P inverse, then you will get Y of t is equal to R of t. This is a simple controller, open loop controller. But in general, you don't have such kind of precise knowledge of the plant. So that's the reason we'll go for a closed loop system. So the closed loop system can stabilize the system, it will reject the disturbances, and also it will track the input signal. We also learned about the different signal types. Currently, I'm not looking at these. All are basic definitions. You can already have gone through it. Now, the next step in this lecture is time domain versus frequency domain. So sometimes signals we can represent in time domain means the variation of signal with respect to time, or we can represent a signal with respect to frequency. How the signal changes with respect to frequency, that is frequency domain. But actually, there are sometimes it will you will have certain advantages if you analyze the system in frequency domain then time domains. In this case, we will learn about Laplace transform. So Laplace transform is a generalized version of expressing the signal in frequency domain. Standard test signal, you also learn about the test signals. Basically, you are having three types of standard input signal. One is a step impulse response, impulse input, which is defined as delta t equal to 0, sorry, delta t equal to 1 for t equal to 0 and it is 0 for otherwise. And unit step u of t is equal to 1 for t greater than or equal to 0 and 0 for t less than 0. And ramp signal r of t equal to t for t greater than or equal to 0 and 0 for t less than or equal to 0. So these are the standard input signals, test signals which we use in the control systems. User. Then you will go into systems response. System response. Let us suppose um, you are having a system like this, and this is your response. Suppose if you give input as impulse, then your what is the response you are getting is called h of t. This is called impulse response of a system. Suppose for what is the response of a system for any arbitrary x of t. So because this is represented by y of t is equal to integral minus infinity to infinity x of tau h of t minus tau dt. Okay, here we are actually saying this will be applicable only if your system is linear time invariant system, because we are actually the impulse are shifted by time and adding with the magnitude x of tau, right? So this will be only applicable if your system is linear time invariant system. So this looks like your convolution integral, that means x of t convolution with h of t. Okay, let's have some example problem. Let us suppose if you are having two signals. This is pretty similar to convolution integral where with x1 of t and x2 of t are two signals. Then convolution of these two are defined as x1 of tau into x2 of t minus tau into d tau. Let's take one example. Let's say x1 of t is equal to u of t and x2 of t is equal to u of t by t plus 1. Then convolution of x1 of t into x2 of t is equal to integral minus infinity to infinity u of tau x1 of tau into x2 of t minus tau theta. So this is equal to so since convolution is a commutative, I can even write as x1 of t minus tau x2 of t minus x2 of tau theta. So it is equal to minus infinity to infinity u of t minus tau u of tau by tau plus 1 theta. How the u of tau looks like? So this is 0, this is tau and 1. So this is u of tau, right? Now u of t minus tau. So u of t minus tau starts at tau is equal to t, right? And it is different for all negative values of tau. So if you multiply u of t minus tau and u of tau, then you will get signal like this, right? So the convolution integral, your limits will be 0 to t instead of minus infinity to infinity. Then u of t minus tau into u of tau, because magnitude is 1, then you will get 1 divided by tau plus 1 theta. Now the integral for 1 by t plus tau is equal to ln of tau plus 1 with limits 0 to t. That is equal to ln of t plus 1, right? Ln of 0 is equal to 1 is 0. So this is your convolution. Now suppose if you go to system response, it is very similar to convolution integral. Let us suppose we are having a system with impulse response h of t. h of t is equal to um, h of t equal to e to the power of minus 2t u of t, and your input is x of t is equal to cos t into u of t. Then you need to find out what is response y of t. Basically, you are having a system with impulse response h of t, and you are having x of t, and you need to find out y of t. Since you know that the response of a system y of t is convolution of impulse response and input x of t, then we can write it as x of t and h of t minus tau beta. Is cos tau u of tau into e to the power of minus 2 into t minus tau u of t minus tau beta. Since the product of u of tau and u of t minus tau is a unit signal, unit sorry unit step that will have limits from 0 to 1, right? So integral 0 to t. And now I am removing that u of t and u of t minus tau. So you will have cos tau into e to the power of minus 2 into t minus tau theta. So I'm taking out e to the power minus t because it is independent of tau. Cos tau e to the power minus 2 tau theta. You know the formula of integral of e to the power of at, integral of e to the power of at cos bt dt equal to e to the power of at by a square plus b square into a cos bt plus b sin bt. Right? Now apply the same formula here. It is e to the power of minus t, e to the power of minus 2 tau by 2 square plus 1 square into a cos is 2. Are you following? Hello?
Yes, ma'am.
Yeah, fine. Here it is e to the power of 2t, right? Tau. Here it is plus. That means now 0 to t into e to the power of 2 tau by 2 square plus 1 square into 2 cos tau plus sin tau. Right? Limits are 0 to t. It has e to the power of 2t I am taking common. So e to the power of minus 2t into e to the power of, we substitute limits, e to the power of 5, 2 cos t plus sin t minus, we substitute 0, sin 0 is 0. Here 2 only we will get, right, here. So we will get 2 by 5. So that means you will have the solution is 1 by 5 into 2 cos t plus sin t minus 2 into e to the power of minus 2t by 5. Fine? So now you should have understand that how painful this convolution and all, right? It taking a lot of time to integrate and do signal shifting operations and all those things. So we'll have one better approach than doing in time convolution is the frequency domain. Doing the same operation, finding the response of the system in a frequency domain for a given input signal in frequency domain. So that will give you much more benefits, especially in computation wise. So in that case, one tool which we learn here is Laplace transform. You already know, right? Laplace transform is a generalized form of representing a signal in frequency domain. Why it is? Because it only decompose the signal. It's also why we are using, why in this class you only focus on Laplace transform is Laplace transform actually decompose, not only decompose the signals into sinusoidals, but also it tells how the sinusoidals are growing or decaying. So that the definition of Laplace transform is Laplace transform of x of t equal to x of s, that is equal to minus infinity to infinity x of t e to the power of minus st dt, where s is equal to sigma plus j omega. So this is called the complex uh, frequency domain, where x-axis is the real part, sigma, and y-axis is the imaginary part. This is called S-plane. In future and all, we use this kind of representation. Let's just take one example to solve the Laplace transform. Let us suppose x of t is equal to e to the power of t into e to the power of minus t u of t. Then Laplace transform of x of t, that is equal to x of x, is equal to minus infinity to infinity x of t into e to the power of minus st dt, which is equal to minus infinity to infinity 2 into e to the power of minus t u of t into e to the power of minus st dt. Okay. So u of t is defined from 0 to 1 and 0 to infinity only. So it is equal to, and also having a magnitude of 1. So we can simply replace the limits, lower and upper limits by integral 0 to infinity t into e to the power of minus e to the power of minus t into e to the power of minus st dt. So this is equal to integral 0 to infinity t into e to the power of minus of 1 plus s t dt. Now to integrate this one, you will use UV formula. This is your U and this is your V, dV. That means, uh, so dV equal to e to the power of minus of 1 plus s into t plus s. Then your V will be e to the power of minus of s plus 1 t by minus of 1 plus s. Right. So using this formula UdV, the formula is integral UdV equal to UV minus integral VdV. So, so the integral is U into dV e to the power of 1 plus s dy minus 1 plus s with limits 0 to infinity minus integral of 0 to infinity e to the power of minus 1 plus s t by minus of 1 plus s dt. Now here if we substitute upper and lower limits in the first part, e to the power of minus infinity is 0, and if you substitute t here, we will be 0, right? 2 zeros minus, here the integral of this one is e to the power of minus of 1 plus s t by 1 plus s whole square with limits 0 to infinity. So you will have 0 If you substitute again the lower upper limit, here it will be 0, then 0, okay, 1 plus plus 4 square, that is equal to 1 by 1 plus 4 square. So this is the Laplace transform of your signal uh, x of t equal to t u of t e power minus t ut. Now in the Laplace transform, we need to define the region of convergence. The region of convergence is tells you in which area the Laplace transform is exists. That means how when this integral converges to convergence. Because in your Laplace transform, we are having two things. One is it is changing from minus infinity to infinity, and at the same time it has e power minus st. So that means it can take values from minus infinity to plus infinity, right? Suppose if x is equal to negative, then this will be e power at and e power st. Then if you put t equal to tends to infinity, then this will become infinity. Like so, we need to define a Laplace transform such that the integral exists. How do you find the ROC? To find in order to find ROC, we will say right minus infinity to infinity x of t e to the power of minus sigma t, where because x is equal to sigma plus j omega, right? So we take the magnitude of e power sigma. This is because this is j omega, e power j omega is the sinusoidal signal, so it won't explode. But only thing is sigma. So that is the reason magnitude of e to the power of sigma t should be less than infinity. You know, right? If e power a t integral of minus infinity to infinity e power a t or general, let's say e power a t. If a is greater, it will rise if a greater than 0, right? E power at will decay, that means it will go like this if a is greater than 0. And if a is less than 0, then it will decay. So using this one, we can say that in your expression where x of t is equal to t into e power minus t ut, if you substitute this one, then integral minus infinity to infinity t into e to the power of minus t into e to the power of minus st dt. Sorry, e to the power of sigma t. It should be less than infinity. That implies e to the power of infinity to infinity into e to the power of 1 plus sigma E should be less than infinity. So when this exponent will become positive, if it is uh, because this is already negative, this should be positive, right? Then only your signal will decay. So that means 1 plus sigma should be greater than positive. That means sigma should be greater than minus 1, or real part of S should be greater than minus 1. So this is the region of convergence. Convergence for this problem. Okay. So as of now, we have gone through. So in this class, we have gone through signals. What are the typical signals we have gone, and what is the difference between open loop and closed loop, and different time domain versus frequency, standard test signals, and convolutional system response. And we also gone through definitions of Laplace transform, right? So in the next class, we will go through some properties of the Laplace transform and how to solve the problems based on the properties of Laplace transforms. And then we will go through inverse Laplace transform and solutions of ODEs using Laplace transform. Have any other doubts? Is it clear now? Hello? Have any doubts?
Yes, ma'am.
Ask me if you have any doubts. Everything is clear now? Okay, next class we will go through the problems on inverse Laplace transforms and properties of Laplace combinations. Is it fine?
Ma'am, actually, your voice is breaking. Can you tell again what you are telling?
Okay. I guess this is fine. I thought. Okay. So could have tell this one before actually. Are you gone through the? Are you understand? Did you understand the class?
Yes, ma'am. Uh, all are okay. All I have understood.
Okay. Next class, I will take care of the volume and all. Might be some breaking network is not good.
Yes, ma'am. A bit of issue.
Yeah, yeah, yeah. I think the signal is a little bit poor from my side. I will take care of this one from the next class.
Okay, ma'am. There will be surprise quiz today, right?
No, tomorrow I will give you next class. I will give
Okay.
it tomorrow.
One more thing, ma'am.
Uh,
The Wednesday class that is Wednesday.
uh,
Actually, I have the DSP,
oh,
and the class timing is colliding. The DSP class is starting from the 6 p.m. for the Wednesday.
okay, okay. I will talk to the POC, then I will change.
Yes, ma'am.
Mm,
Okay, ma'am.
okay, okay. So what other classes we are having other than this one? Because 5:30 is the time actually we are planning. 5:30 to 6:30.